Hello everyone, I will present our paper entitled An Improved Ant Colony System to Solve the Time-Dependent Orienteering Problem. I start with an introduction and then I will talk about the previous method and the method we proposed and compare the results. Today, with the growth of cities, transportation plays an important role in real-world problems. Therefore, routing problems are important for managing time, cost, and distance. In some routing problems, such as TSP, the goal is to find the shortest path by visiting all vertices. But in real-world problems, there are often limitations and all vertices cannot be visited. To solve this problem, orienteering problem was introduced in 1985. Orienteering problem takes these constraints and is closer to the real-world problem. This problem has several generalizations for different applications. One of them is a time-dependent orienteering problem, which was introduced in 2002. In time-dependent OP, travel time between two vertices is not constant at different times. This problem is very close to real-world routings and has different applications. In time-dependent OP, we have a complete graph. In this graph, the start and end vertices have zero profits, and other vertices have different profits. We also have a time limit for travel. In this problem, the travel time between two vertices is not constant at different times and changes based on network details such as traffic. For example, in the speed model used in this table, with the traffic amount, 4 time periods and 5 categories are defined for the edges. Each edge has a category. Based on this category, edge has a different speed in each time period. With these details, in time-dependent OP, I'm at finding the path from the starting vertex to the ending vertex, such that the total profit becomes maximum and the travel time doesn't violate time limit. The time-dependent OP applications get closer to real problems. Transportation networks and tourist planners are the problems modeled by time-dependent OP. One dataset for the time-dependent OP was introduced in 2014. This dataset is modeled by a traffic amount at different times on the network. This dataset includes 7 networks with the number of vertices from 21 to 102. Previously, an ant colony system has been introduced to solve the time-dependent OP. In our paper, an improved version of this algorithm is proposed. This slide is the previous I-ACS algorithm. In this algorithm, first, the Fermat value is adjusted by initial tau and the greedy information is calculated by a score to distance ratio. Then the initial routes are constructed. Construction of the initial routes starts with a route where the starting vertex is 1 and the ending vertex is n. Until the time limit of the problem allows, by LI probability and relative selection, one vertex is selected and added at the end of the route. Then, the pheromone value of the edges in the rows are evaporated. In the local search phase, first, 2-opt tries to reduce the travel time, and then insert tries to increase the total score by adding new vertices. In each iteration, the route with the maximum profit is saved, and in the global pheromone update, the pheromone value of the edges of this route is increased. At the end, all steps are repeated 133 iterations. But if no improvement in 25% of the total iterations, the pheromone value of the edges is changed to initial term. We improved the several phases of the algorithm. For concept initial solutions, in the previous method, grid information was the ratio of the score to distance. But in this example, we can see if we want to go from vertex 1 to vertex 2 or vertex 3, because the distance to vertex 3 is less, the vertex 3 is selected. But by according to speed, the vertex 2 is better. To solve this problem, we included speed in this formula. In the local search phase, we applied insert and replace. Our proposed insert is a combination of 2-opt and adding a new vertex. First, 2-opt is applied, and after adding a new vertex, 2-opt is applied to the new route. This method continues and is stopped where there is no progress. Replace tries to replace a vertex in the current route with an unvisited vertex having a greater score. To decrease the computation time, replace is applied only to the best route of each iteration. In global pheromone update, we increase the pheromone of the edges of the best path in the current iteration. This is the ratio of the profit of the best path in the current iteration to the profit of the best path in all iterations. At the end, all steps are repeated 100 iterations. But if no improvement in 50% of the total iterations, the pheromone values of the edges in the best path is changed to initial term, and other edges is changed to initial tau plus rho. Rho is evaporation rate. All experiments were performed on a system with an Intel Core i7 with 3 GHz processor and 16 GB memory. We have two benchmarks. Benchmark 1 includes 24 instances, and the gaps for the 14 instances are 0 for I-ACS and I-ACS algorithms. The remaining 10 instances are in this table. N is the number of nodes, T is the time limit, Best gap and average gap are the best and average gap between 5 solutions and CPU is the program execution time. The I-ACS has reduced the gap of 7 instances to 0, and the average gap has reduced from 0.2 to 0 in the best state and from zero point 0.8 to 0.2 in the average state. Benchmark 2 includes 59 instances. The gaps of 26 instances are 0 for I-ACS and ACS algorithms. After remaining 33 instances, the I-ACS algorithms has better results, and only in 5 instances has worse results. The average gap has been reduced from 1 to 0.5 in the best states and from 1.4 to 0.8 in the average state. Thank you for your attention.